Across the high desert of central New Mexico, the landscape appears calm. Vast stretches of sunlit plains extend toward distant mountain ranges. Dry winds move across sagebrush and grasslands. Small communities go about their daily routines beneath immense skies that seem unchanged by time. Yet deep within the earth, far below the mesas and valleys surrounding Socorro, forces of extraordinary scale are stirring beneath one of North America's most intriguing geological mysteries. For generations, the region around Socorro has occupied a unique place in the scientific imagination. Instruments designed to listen to the subtle movements of the planet have repeatedly detected something unusual beneath this part of the American Southwest. Earthquakes occur with remarkable frequency. The crust appears to deform in ways that suggest pressure is building from below. Seismic waves traveling through the subsurface reveal a vast zone unlike ordinary rock. Scientists now know that this feature is not merely a localized pocket of molten material. It is an immense body of partially molten rock extending across a significant portion of central New Mexico. Known as the Socorro Magma Body, it represents one of the largest active magma accumulations recognized within the continental United States. Recent earthquake swarms have drawn renewed attention to this hidden giant. Clusters of tremors have rattled the region, prompting geologists to examine an important question. Are these earthquakes simply part of a long-established pattern of tectonic activity, or are they signs that deeper changes are underway within the magma system itself? The answer remains uncertain. Yet uncertainty has never prevented scientists from looking closely when the Earth begins sending signals. Far beneath Socorro, at depths of approximately 12 to 15 miles, or about 20 to 24 kilometers, lies a layer unlike the solid crust surrounding it. This region contains partially molten rock, spread across an area covering thousands of square miles and thousands of square kilometers. Rather than existing as a vast underground ocean of liquid magma, the material resembles a complex mixture of crystals, molten rock, and gases trapped within a network of interconnected spaces. The discovery emerged through decades of careful observation. Seismologists noticed that earthquake waves behaved strangely when passing through the region. Some waves slowed dramatically. Others reflected from hidden boundaries deep underground. Additional measurements revealed that parts of the crust above the magma body were gradually rising. Such uplift is among the most important clues available to volcanologists. When magma accumulates underground, it can exert pressure on overlying rocks. In some volcanic systems, this pressure causes the surface to swell upward by measurable amounts. Satellite observations and precision ground measurements have demonstrated that portions of the Socorro region have experienced gradual uplift over extended periods. The movement is subtle. Most residents would never notice it. Yet geological processes often unfold on timescales far beyond ordinary human perception. A few millimeters each year may appear insignificant. Over decades and centuries, however, those tiny increments can reveal profound activity occurring far below. Earthquake swarms add another layer to the puzzle. Unlike a single large earthquake followed by aftershocks, a swarm consists of numerous earthquakes occurring within a relatively confined area over a limited period. Such swarms can arise from many different causes. Stress adjustments along faults may trigger them. Fluids moving through fractures can generate them. Magmatic systems frequently produce them as molten rock and volcanic gases alter underground pressures. The challenge facing researchers is determining which mechanism dominates at any given moment. In volcanic regions around the world, earthquake swarms have often preceded significant eruptions. They occurred before eruptions in Iceland. They have been documented beneath volcanic centers in Japan, Italy, Alaska, and elsewhere. Rising magma can fracture surrounding rocks, producing distinctive seismic patterns that alert scientists to changing conditions. Yet swarms alone do not guarantee an eruption. Many volcanic systems experience episodes of unrest that never culminate in surface activity. Magma may shift underground, pressure may increase temporarily, and earthquakes may proliferate without any lava reaching the surface. Distinguishing between routine unrest and meaningful escalation remains one of the central challenges of modern volcanology. The Socorro Magma Body occupies a particularly fascinating geological setting. It lies within the Rio Grande Rift, a massive zone where the Earth's crust is gradually stretching apart. This rift extends from Colorado through New Mexico and into northern Mexico. Unlike the dramatic boundaries where tectonic plates collide or slide past one another, the Rio Grande Rift represents a region where continental crust is slowly being pulled apart. As the crust stretches, fractures develop. Hot material from deeper levels of the Earth can rise more easily. Over millions of years, these processes have contributed to volcanic activity across the Southwest. The volcanic history of New Mexico is far richer than many people realize. Ancient lava flows, volcanic fields, cinder cones, and calderas are scattered throughout the state. Several enormous eruptions occurred during the distant past, reshaping landscapes across hundreds of miles and hundreds of kilometers. Ash from prehistoric eruptions once drifted across large portions of North America. One of the most spectacular examples is the Valles Caldera in northern New Mexico. Formed approximately 1,200,000 years ago, this immense volcanic depression marks the site of a colossal eruption that expelled vast quantities of magma. Even today, geothermal activity continues within the region, reminding visitors that volcanic systems can remain active long after their most dramatic eruptions. The presence of the Socorro Magma Body raises an intriguing possibility. Could the region eventually develop into a future supervolcanic system? The term supervolcano refers not to a specific volcano, but to an eruption capable of ejecting more than 240 cubic miles, or roughly 1,000 cubic kilometers of volcanic material. Such eruptions rank among the most powerful natural events known on Earth. The eruption of Toba in present-day Indonesia approximately 74,000 years ago released extraordinary volumes of ash and volcanic debris. Yellowstone's prehistoric eruptions likewise produced caldera, forming events that transformed enormous regions. These rare catastrophes occupy a category entirely different from ordinary volcanic eruptions. At present, there is no evidence that Socorro is approaching such an event. That distinction is critical. A large magma body does not automatically become a supervolcano. Most magma reservoirs never generate supereruptions. Many cool and solidify without producing major surface activity. Others feed smaller volcanic eruptions spread across extensive periods. Nevertheless, the size of the Socorro system attracts scientific interest because it demonstrates that substantial amounts of molten material continue to exist beneath central New Mexico. Recent earthquake activity has therefore become part of a larger effort to understand how magma systems evolve over time. Modern monitoring technology provides capabilities unimaginable only a few decades ago. Networks of seismometers detect tiny earthquakes that would otherwise pass unnoticed. Global positioning system instruments measure crustal movements with astonishing precision. Satellite radar can identify subtle surface deformation across broad regions. Geochemical analyses reveal changes in underground fluid systems. Together, these tools allow researchers to build increasingly detailed pictures of hidden processes occurring miles below the surface. Each earthquake recorded beneath Socorro becomes a data point. Scientists examine its location, depth, magnitude, and relationship to surrounding seismic events. Patterns emerge gradually. Some earthquakes cluster along known faults. Others appear near zones associated with magma accumulation. The deeper question concerns energy. Magma contains enormous amounts of thermal energy. Even partially molten rock remains capable of influencing surrounding crust. As heat transfers into adjacent rocks, fractures may form. Fluids can circulate through newly created pathways. Pressure changes may propagate through extensive underground networks. Viewed from the perspective of geological time, volcanic systems behave less like static structures and more like living entities. They grow, evolve, migrate, and occasionally awaken after long periods of apparent dormancy. Many of Earth's most famous volcanic centers spent thousands or even hundreds of thousands of years in relative quiet before producing significant eruptions. Such timescales challenge human intuition. Civilizations rise and fall within intervals that may represent only brief moments in the lifespan of a volcanic system. This reality contributes to both the fascination and difficulty of assessing volcanic hazards. No scientist can state with certainty whether the current earthquake swarms beneath Socorro represent routine activity or the earliest stages of a long-term transformation. The available evidence supports caution rather than alarm. Earthquake swarms have occurred in the region before. Uplift has been documented for decades. The magma body itself has likely existed for millions of years. Yet geology teaches a humbling lesson. Systems that appear stable may conceal processes unfolding beyond direct observation. Far below New Mexico's deserts, temperatures remain high enough to keep portions of rock partially molten. Pressure continues to accumulate and dissipate through natural cycles. Earthquakes periodically remind observers that the crust is neither motionless nor permanent. For residents of Socorro, the tremors may feel like brief interruptions. For scientists, they are messages arriving from deep within the planet. Every seismic pulse carries information. Every subtle rise of the land records a change in underground conditions. Every new measurement contributes to a growing effort to understand one of North America's most enigmatic magma systems. The coming years may reveal that the recent swarms are merely another chapter in a long history of geological restlessness. They may indicate pressure adjustments within a stable magma body. They may reflect interactions between tectonic stretching and deep crustal processes that have operated for countless generations. Or they may represent the earliest detectable hints of a volcanic future still hidden beyond the horizon of current understanding. The Earth rarely announces its intentions clearly. Instead, it whispers through vibrations, deformation, heat, and time. Across central New Mexico, those whispers are being recorded with unprecedented precision. Scientists continue listening carefully, aware that some of the most important geological transformations begin not with dramatic explosions or towering plumes of ash, but with subtle signals emerging from darkness far below the desert floor. There, within the immense Socorro Magma Body, one of North America's greatest geological mysteries continues to evolve. Pulse by pulse, earthquake by earthquake, as researchers strive to determine whether they are witnessing ordinary unrest or the earliest stirrings of something far more significant. The possibility draws attention because the Socorro Magma Body occupies a stage in volcanic evolution that remains imperfectly understood. Geologists have identified giant magma reservoirs beneath several regions of the world, yet the path from a deep accumulation of molten rock to the birth of a major volcanic center is neither straightforward nor predictable. The Earth does not follow a script. Every volcanic province develops according to a unique combination of heat, pressure, chemistry, tectonic forces, and time. Time may be the most important ingredient of all. Human beings often think in years, decades, and occasionally centuries. Volcanoes operate according to clocks measured in tens of thousands, hundreds of thousands, and millions of years. The magma beneath Socorro may have been gathering, cooling, reheating, and reorganizing itself long before the earliest humans crossed into North America. Processes occurring today may not reach their ultimate conclusion until a future so distant that present civilizations exist only as archaeological traces. That immense scale complicates efforts to interpret modern seismic activity. An earthquake swarm that appears dramatic on a news report may represent only a minor fluctuation within a geological system of staggering dimensions. A cluster of hundreds of earthquakes sounds alarming until it is compared with the countless fractures, adjustments, and pressure changes continuously occurring within the crust. Volcanologists therefore focus not merely on the existence of earthquakes, but on their characteristics. Depth matters, location matters, frequency matters. Changes in those patterns often matter most of all. When magma begins moving upward through the crust, earthquake depths sometimes migrate toward the surface. Tremors may become increasingly concentrated along specific pathways. Ground deformation can accelerate. Volcanic gases may emerge in greater quantities. Thermal anomalies can appear as underground heat approaches shallower levels. Scientists searching for signs of genuine escalation therefore examine multiple indicators simultaneously. One signal alone rarely provides definitive answers. Several signals changing together attract far greater attention. At present, researchers studying Socorro continue to evaluate whether recent activity fits within established patterns or represents something new. Part of the concern stems from the sheer size of the magma body itself. Seismic imaging studies suggest that the partially molten zone extends across an area measuring dozens of miles and dozens of kilometers in width. Although much of the material consists of crystal-rich mush rather than fully liquid magma, the total volume remains immense. Such reservoirs act as long-term storage systems capable of accumulating additional molten rock delivered from deeper levels of the Earth. The image often imagined by the public, a gigantic underground lake of glowing magma, is misleading. Natural magma systems are considerably more complex. Imagine a sponge saturated with liquid rather than an open pool. Crystals occupy significant portions of the volume. Molten rock fills spaces between those crystals. Gases become trapped within the mixture. Temperatures vary from place to place. Some regions remain nearly solid, while others contain larger fractions of melt. This distinction is important because magma must often undergo substantial changes before an eruption becomes possible. A reservoir containing only a modest percentage of molten material may remain stable for extraordinarily long periods. Additional heat or fresh magma injections can increase the proportion of melt. Pressure can rise. Chemical interactions may alter the behavior of the system. Over time, conditions may evolve toward greater mobility. The process resembles the gradual preparation of an engine rather than the flipping of a switch. Evidence from volcanic provinces around the world suggests that large eruptions frequently require repeated injections of fresh magma from deeper sources. Each new influx contributes heat and material. The reservoir becomes increasingly energized. Pressure builds incrementally. Researchers therefore pay close attention to signs that fresh magma may be entering existing storage zones. Earthquake swarms occasionally provide clues. As molten rock forces its way into fractures, surrounding rocks respond. Some crack under stress, others bend. Entire sections of crust may shift by tiny amounts measurable only through sophisticated instruments. These responses create seismic signatures that trained scientists can analyze. The challenge is that tectonic stretching associated with the Rio Grande Rift can produce many of the same effects. The region is already geologically active. Faults continue adjusting to crustal extension. Earthquakes occur even in the absence of significant magmatic movement. Distinguishing one source from another requires extensive analysis. This uncertainty has led some experts to adopt a cautious but measured perspective. Many researchers emphasize that unrest does not necessarily imply danger. Active volcanic systems commonly experience fluctuations without progressing toward eruption. Yellowstone provides an instructive example. The famous volcanic plateau experiences frequent earthquake swarms, measurable uplift and subsidence, and ongoing geothermal activity. Yet despite decades of public speculation, no evidence indicates that a catastrophic eruption is imminent. The lesson from Yellowstone is not that volcanic systems should be ignored. Rather, it demonstrates that geological activity and impending disaster are not synonymous. The same principle applies to Socorro. Still, the region differs from Yellowstone in important ways. Yellowstone possesses abundant surface expressions of its underlying heat. Geysers erupt, hot springs bubble, steam vents release gases. Visitors can witness direct manifestations of the volcanic system. Socorro offers far fewer visible clues. Most evidence for the magma body comes from instruments rather than surface features. The hidden nature of the system contributes to its mystique. Vast quantities of molten material exist underground, yet the landscape above appears deceptively ordinary. Such contrasts have occurred throughout geological history. Several of Earth's great volcanic provinces began their development long before dramatic surface expressions emerged. Deep reservoirs accumulated heat and magma over immense periods. Gradually, fractures expanded. Pathways formed. Smaller eruptions sometimes preceded larger events by thousands or tens of thousands of years. Volcanologists studying ancient calderas often reconstruct these sequences from layers of rock and ash preserved in the geological record. Those records reveal that supervolcanoes do not appear overnight. Before the largest eruptions, signs of magmatic evolution typically unfold across enormous spans of time. Reservoirs grow. Crustal structures weaken. Multiple episodes of magma intrusion reshape underground architecture. The eventual eruption represents the culmination of a lengthy process, rather than an isolated event. This understanding has led many scientists to view the Socorro Magma Body as a laboratory for observing early-stage magmatic development. Even if no eruption occurs for many thousands of years, the system provides valuable insights into the formation of large magma reservoirs. Every earthquake swarm, every millimeter of uplift, and every new seismic image contributes to a more complete understanding of continental volcanism. The implications extend far beyond New Mexico. Across the globe, millions of people live near potentially active volcanic systems. Improving the ability to distinguish ordinary unrest from meaningful escalation remains a major scientific objective. Knowledge gained from Socorro may eventually enhance monitoring efforts in regions facing more immediate volcanic hazards. Meanwhile, advances in technology continue revealing details that previous generations could scarcely imagine. Seismic tomography now allows researchers to construct three-dimensional images of structures hidden deep within the Earth. Much like medical scans reveal organs inside the human body, these techniques illuminate magma reservoirs concealed beneath miles of rock. The resulting images portray a dynamic underground environment. Some regions appear hotter than others. Certain zones contain higher percentages of molten material. Pathways potentially connecting deep magma sources to shallower levels become visible. Each improvement in resolution sharpens scientific understanding. Yet every answer seems to generate new questions. Where exactly does the magma originate? How rapidly is it replenished? Has the reservoir been growing, shrinking, or remaining relatively stable? Are current earthquake swarms linked directly to magmatic processes, tectonic forces, or a combination of both? These questions occupy researchers because the stakes associated with volcanic forecasting are enormous. Fortunately, available evidence indicates that no such event is imminent beneath Socorro. Scientists repeatedly emphasize this point because public fascination with supervolcanoes often outpaces scientific reality. Large magma reservoirs do not automatically translate into immediate danger. Geological systems evolve slowly. Detectable warning signs would almost certainly precede any major eruption. Monitoring networks exist precisely to identify those changes. If magma began rising significantly toward the surface, instruments would likely record corresponding shifts in seismicity, deformation, and other indicators. Modern volcanology has advanced dramatically compared with earlier eras when communities sometimes received little warning before eruptions. The Earth remains capable of surprising researchers, but scientific awareness has never been greater.